Okay, so let's just spend some time on the Zener diode now. Now, when we look above on the breakdown mechanisms, remember we talk about the Zener breakdown, and we mentioned about the Zener breakdown mechanisms to be because of heavily doped uh, semiconductors, be it the N-type or P-type, and this leads to a very small value of D, and the electric field is high. This is why we have a Zener breakdown. Yeah, this is why you still have this mentioned the heavily doped silicon or germanium p-n junction. Yeah. Now, what is important to recognize about the Zener diode? It is very similar to your normal diode. What we've studied till now is we can represent your normal diode ideally as a short circuit or as an open circuit. So this is going to be very similar for the Zener diode, except for the breakdown region. Remember, we have a region where it's called breakdown, where normally a normal diode will not operate because this is going to mean the diode is totally damaged. You can't use it anymore. But this is the advantage of a Zener diode. You can actually operate your diode in that region itself without damaging it. And if you want to invest in additional expenses for buying a Zener diode, it's because you want it to be in that region. Because if you don't want to operate your diode in that region, you will simply use a normal diode. This is important. Yep. So a Zener diode is shown like this. You have a same symbol as a normal diode, except you have two small bars there to show that it is Zener diode. So this is going to be the symbol now for a Zener diode. Yep. And you can see there are many ranges shown there. So when you go in the market and you look for Zener diodes, you can find diodes rated at 2.4 volts to 200 volts. What is this 2.4 volts? It's not the forward breakdown. It's actually the voltage at which the diode would have the vertical part. Yep. Let me go up completely and show that to you. It's not in this one. Let me just go to this one. This is a very important observation you have to understand well. So you're seeing that now, when I talk of 2.4 volts, I'm talking of a breakdown voltage here. So this value is at minus 2.4. This is where the voltage would more or less stay fixed. Can you see when you come in breakdown here in a Zener diode, your voltage is remaining fixed at the breakdown voltage. If it is 2.4 volts, it means the moment you exceed 2.4 volts, it would not be exceeding 2.4 volts. It's going to maintain 2.4 volts. So immediately this would be beneficial to be used as protection. So if you have a certain device you want to protect against overvoltage, you can connect it across a Zener diode. The moment the voltage goes beyond a certain voltage, the Zener diode will not allow this voltage to go beyond that. So already one application for the Zener diode is in safety as a protection for sensitive devices because the voltage can never go beyond a certain value. Yep. So when you talk about breakdown voltage of a wide range there, the 2.4 to 200 is the breakdown voltage. Yep. So we've talked about the Z there, which is in the symbol. Now let's look at the important conditions you would need to bear in mind when you're designing a circuit to use a Zener diode. Yep. So first thing, it should be reverse bias. If you connect a Zener diode in forward bias, it has no purpose because it's a normal diode. So you would typically connect a Zener diode in the reverse mode. Like I'm saying, operating it in the forward mode is nothing but a normal diode operating in forward condition, and hence does not justify the relatively higher cost involved. Yep. So in a circuit, if you see a Zener diode in forward mode, you would say yes, but why don't we use a normal diode? That's all. We have voltage across it greater than Vz. So if you are applying voltage across a Zener diode which is less than the breakdown voltage, again, even if it is reverse biased, but if your voltage is not exceeding the breakdown voltage, it is still a normal diode. So if your applied voltage can never go beyond the breakdown voltage, you would not use a Zener diode. You would simply use a normal diode. So two important conditions say it should be reverse biased so that it goes in breakdown. And second, for it to go in breakdown, the voltage applied across it should be greater than the breakdown voltage. So for example, if I say I'm buying a Zener diode rated at 2.4 volts, I need to make sure that the voltage applied across it in the reverse mode is above 2.4 volts for it to maintain it at 2.4 volts. Yep. So if I go back again to explain this clearly, let's say this is your characteristic for this diode, and I'm applying a voltage of 5 volts. When the breakdown is at minus 2.4, it would not go to 5 volts. It's going to maintain it at minus 2.4 volts. This is what you're saying. So you have to make sure that you're not operating here. If you're somewhere here, which is a normal diode, normal everywhere, you have to make sure the applied voltage is beyond the breakdown voltage for it to be functional in the breakdown region. So it means is in diode we have 3 operating regions: the forward mode, the reverse mode, and the breakdown mode. Whereas in normal diode, you will not talk of breakdown mode because it would have been damaged. Whereas this diode can operate in the breakdown region. That's important to me. Now let's go back to a third important characteristic. You will tell me this, but when will the diode get damaged? Because you can operate at any voltage you want in the reverse direction. Is it damage free? So you have to be careful about one important parameter. The current that can flow in the breakdown region should not exceed a given parameter, which is given in the data sheet. So it means when you are designing for a diode, you would have to first make sure it is reverse biased. That's the first thing. Second thing, the voltage across it is greater than the breakdown voltage. That's fine, but you need to calculate the current that is flowing through it. It should not exceed a given maximum. If it exceeds, that current is going to blow it off, because a current creates heat dissipation, and heat dissipation, like I said, you would have a heat sink connected on the diode. That's fine, but the heat sink is able to dissipate a certain amount of heat in watt. If you exceed that amount of heat dissipation, the diode will heat up and blow off. Yep. So it means what determines the heat dissipation is current. So you should not exceed I Z max. Let's take some examples. So this is where we stop. We're going to just take a few examples to actually apply these principles we've just seen above. Let's look at this one. So the question is, check if the following diodes are properly biased, means are they connected in reverse mode? Yep. They're expected to operate in the breakdown region within the permissible current limits. So if you look at the specification on this Zener diode, first thing, the VZ is a breakdown voltage. Yes. Second, you have an IZ max, as we said, so the current flowing in this circuit should never exceed 4 milliampere. Okay. Now let's see, applying these three rules there. First, it should be reverse biased. Is it reverse biased? Yes. Your 15 volts is plus minus, so it is reverse biased. If you reverse the polarity of your battery, then it's wrong, because then it's going to be forward biased. It's no use. Second, have voltage across it greater than VZ. VZ is 12 volts. You're applying 15 volts. Yes, it's possible for it to go in breakdown region because you're exceeding the 12 volts. So that's still good. These first two are correct. The third condition, the current that's going to flow should not exceed 4 milliampere. How do we calculate that? So we know in breakdown region, you would always have 12 volts across it here. You're applying 15 volts, so remaining 3 volts have to be across the 330 ohms. So you use now Ohm's law. If you have 3 volts drop across 330, just do 3 divided by 330, if I just do that. So since the resistor and the diode are in series, the same current has to flow through them. So 3 volts, which is a drop across your 330 ohm resistor. Why? Because you have 12 volts across your diode, simply because it is in breakdown region. It's going to maintain 12 volts. That's a very important characteristic of this diode. It's going to maintain a voltage across it, which is limited by the breakdown voltage. You can never have 13 volts across this diode. As you see in the curve, it goes very steep down. Okay, so if you have 12 volts there, the remaining 3 volts need to be across the 330 ohm resistor. V is equal to IR. Your I is V divided by 330. So you get a value of 0.009 ampere. And when you convert to milliampere, you're going to get 9 milliampere. So it means you are exceeding that value. Yeah, I've just taken 3 divided by 330 and then times 1000, you get 9 milliampere. So this circuit, even if it is properly biased, even you are exceeding the breakdown voltage, but that current limit is not sufficient, you would need to upgrade that. So you need to choose a diode which is at least 10 milliampere here. Else this would break. This diode is going to be damaged in this circuit. So in this case, you would say this is not properly designed because you're exceeding your 4 milliampere. Let's do one more, and then I'm going to leave these two for you to try. Yep, let's do this one. So now you have 6 volts here, and you're applying, you have 6 volts supply connected positive, negative. Your VZ is 10 volts. Your IZ max is 7 milliampere. Yep. So first observation about the polarity, yes, it's positive, negative. It is reverse biased, but the second condition is not proper. With 4 volts, you can never achieve 10 volts in breakdown. If I go back here, you are somewhere here. You are not able to come to the minus 10. So it means this is not properly biased. You are wasting the use of a diode in this case. In that case, it would never actually be going into breakdown, and you won't get a current flowing. So there's no purpose in checking for the maximum current. This will never go in that mode. So this is, again, not properly designed. If you look at this one, 15 volts here. If you look at the polarity of the battery itself, it's not proper. You're connecting here in a mode where it's positive. So this diode is simply in forward mode. So current will flow like this. This becomes forward mode. It's a normal diode. You're again wasting your money in investing in diode like this. Unless your 15 volts is like this here, then yes. But this one is not properly biased. Okay, so we've seen this one, the problem is about the current. This one, the problem is about the voltage. This one is the problem about the polarity. Let's look at this last one here, and we end for today. So if you look at the polarity, first, the way it's connected. If you have 24 volts there, current would try to flow like this. You can see these two are in parallel, so current is going to split into two here. Yep, but the same main current has to flow here and then get split into two. Yep, and then would flow here. When will this happen? Of course, you need to have a voltage here which is above 12 volts, else it would not be in breakdown region. It's only in breakdown region that current flows across the diode. In reverse mode, it's become an open circuit, so you won't have any current flowing. It's just going to become a simple series resistance circuit there. Yep. So if you look at the circuit here, you have 24 volts, and 24 volts can exceed 12 volts. So polarity is also okay. 24 volts, it can exceed 12 volts. We have to do some calculation to verify. So it means, yes, it seems to be properly biased, but we need to check the IZ max. Let me just bring that into Paint, and let's do some calculations on here. Yep, like this. Now let's do a calculation to just see what is the voltage drop we are expecting. Let's forget about the diode for the time being. Let's see if we have 1800 ohms here and 1200 ohms, what voltage drop do we expect to get across this one, because these two are parallel. Let's just do a very simple calculation. So voltage across the 800 ohm resistor is going to be 1800 divided by, so it's like a voltage divider, 3000 multiplied by 24 volts. So it's your voltage divider equation. Remember, we've seen that in the fundamentals earlier. I said you'll be using that a lot, so it's good to know it. So let's do 1800 divided by 3000 multiplied by 24. We get 14.4 volts. So it means if you forget about this one here, let's say you forget about the diode, you expect to get 14.14 volts here and the remainder here. But since these two are in parallel, the voltage across the diode will never exceed 12 volts. It means you would never go to 14.4 volts. At this point in time, this is showing that the diode has gone into breakdown. So you're going to measure, if you measure the voltage here, across these two here. Yep, the voltage here. You're going to get 12 volts because you can't exceed the barrier, the breakdown voltage. Now, it means the voltage across the 1800 ohms is not 14.4, actually is limited to 12 volts only. So if 12 volts is here, you would need to have 12 volts across your 1200 ohm resistor, because these two are actually, the 24 volts have to be distributed across these two. So if you have 12 volts across this one and this one, which are parallel, 12 volts have to be here. From this one, you can work out what your main current is flowing. So this one here, you can work out what main current is flowing here. So this is going to be 12 divided by 1200, supply ohms. So you get your 10 milliampere. So 10 milliampere is going to flow the main current. Be careful, 10 milliampere is not the current flowing here, because this current has to split into two here. So next task for you would be to calculate what current flows here. Got a parallel path, you have the current splitting, and then you'll be able to know what current is flowing in the diode. Now, how do we get the current actually flowing through the, how do we get the current flowing in this path there? Again, Ohm's law, we have 12 volts across your 1800 ohm resistor. So again, V is equal to IR. You take 12 divided by 1800 now, you get 6.67 milliamperes flowing here. Now, if you have 10 milliampere coming in and you have 6.67 milliampere coming here, so what is left behind? You apply Kirchhoff's current law. So 10 is coming in, 6.67 here. You need to have 3.33 milliampere moving here. So that when you add the two, you get your original current. And these two current, of course, are going to add back and go to 10 milliampere. So now you check, you find you have 3.33 milliampere flowing here, which is not exceeding your 6 milliampere. So it means you're not exceeding your IZ max. It's fine. It's in the safe limit. So this circuit there, just to recap, this circuit there is properly biased in terms of polarity, in terms of magnitude is also okay. And the current we work out is not exceeding 6 milliampere. So it's properly biased. Okay, so I think we're going to stop here.